happening around 1,000, I'll go from 10, I'll go from about 10 to 10K. I don't know, you can just play around with those values. Okay, start value, end value. And remember now, the horizontal is not radians per second, okay? We're artificially doing it radians per second because there's no way to change the horizontal LT spice to radians per second. So we're doing it by making a list. So it's a trick. Okay? And here it is. Okay? This is your attenuation. And hopefully if I go to 1234, I should see 3 dB. Also, if I go to 1,000, I should see 0.5 dB. If I go to 2,000, I should see something above 20 dB. Everybody understand? It's not difficult at all, but that's how you're going to check your design. So if you do a design, you check it, and you don't get those numbers, something is wrong. Don't just hand that in. Something is wrong. Either something is wrong with the way you're simulating it, or something is wrong with your calculation. You gotta go. You gotta basically close the loop on that one. No pun intended. You gotta go back and find out where the error is. Is it a syntax error in your simulation? Is it a number that you computed wrong in your CAD calculation? Is your omega not wrong? Did you forget to scale that capacitor? I've seen all these things. In fact, I've done all those. That's how I know. But you gotta figure out which one of those things has gone wrong. Okay, so let's take a look closely here. Closer in this range. 1 to 2K, because that's where all the action is really happening. So let's zoom in there. Okay, again, cursor. First let's go to what? 1234. If I go to 1234, take this and watch for the horizontal about 1234, 1.234. Somewhere there maybe. 3 dB. Okay? If I go down to 1K radians per second, 1,000 radians per second, you can almost see it's about a half, right? So it is correct. It should be very close to 0.5. Very close to 0.5. Of course, if you don't take enough points per decade, remember that last number in the HC? If I only take 3 points per decade, it's going to be very choppy and you're not going to get it. So sometimes you increase the resolution or the number of points you take, you might increase that number from 100 to maybe 200. The analysis will still run very fast. These are very fast analysis. So all you got to do is, again, take the cursor, go down to 1,000. I'm watching that horizontal. Go to as close to 1,000 as possible. You won't get 100% in there, but you can see it's about 0.5. It's a little bit above, but it's okay. Okay? You're almost right on the dot, exactly there. Okay? How about 2,000? Let's go to 2,000. Well, it's a little bit out of the range, so let me close this and zoom out and choose that a little carefully. So 2 is over here, 2K. So if I zoom around here, I mean, you can visually almost see that it's at 21, right? See at 2K? It's at 21. It's about 20. I don't need to measure, but if you need to measure it, that's what you would exactly see. You would see that at around 21. You can go to it and roughly take a look. Here we are at 2K, about 21. We are about 20, so this design is done. However, from a component point of view, it's not really done, is it? Because if you go back to your design and take a look, these are 1 ohms. You don't really want that, right? So that's where magnitude scaling comes in. You go and magnitude scale everything. You multiply the R's by Km, we divide the C's by Km. When you do that, it should not change anything that we just seen. If it does, you missed an element or you've done something wrong. Okay? So, you have to go to all the resistors and make them, for example, in this case 10K. Can it be 1K? Sure. You can pick that to be anything. If somebody says make all the final resistors 10K, the answer is already given to you. Okay? Assuming all the resistors are the same to start with. Okay? So, you can go here and change it to 10K. So let me just change this to 10K. Okay, then what I'm going to do is, not 1K. Don't do that. This will give you an error, right? This will give you an error. Let's try it. Actually, it took it. Because the guy who writes it is smart enough to know that people hit the O sometimes, and he knows it's okay. Everybody get that? Alright. Took only a few seconds. Your response time is improving, though. It's good. Alright. So, I mean, I should not have this. That doesn't look. So, 10K. 10K. And then cut these out. And then copy and paste. Use copy, paste. Okay. So you should, if you're not using it already, you should be using some kind of simulation tool anyway. But I'm just showing this to you as well because, I mean, the steps sometimes are maybe not clear to you, but you just have to try it. Okay, so I'm just scaling, magnitude scaling, not everything. I've already done the R's, so I'm just doing the capacitors. Okay, this is by km. Okay, and so this is nice because if I go and a little bit later on change my kf to something else, I don't have to go into each capacitor and put in my values again. You see that? You know, 2.392 nanofarad, and now suppose you make it 352. You know, suppose you make the numbers wrong. You transpose the digits. Or instead of nano, you put micro. You could be off, way off, and that's very hard to find when you have 15 stages. You know, it's like Where's Waldo? You can't find it. So this is a little bit easier. It lets you use the variables. Okay, so I think I have all the resistors, all the capacitors. So now, if I go back here, okay, and rerun the simulation, nothing should change. Nothing should change. If something changes, something went wrong. So I'm going to watch for that now, because I could have done something wrong here. So I simulate it. That's it. Nothing changed. That's good. That's what you want. Alright? So that's your final design. And of course, what are the values? Well, you can calculate the values. Or you can have it in your paper design. Is everyone clear about this? I'm going to post this up. And you can start from this point, okay? Just from this point, and you can do your design. And keep this on there. Because if you don't keep this on there, then you know you have hertz and radians per second, and it hurts when you don't get the number right. There's another good one. Record that one. Okay. So this is the way. This is the way to plot. Do this AC analysis in radians per second instead of hertz. We basically still feed in hertz because LT Spice only understands that frequency value, but we declare this list called W, so omega, and feed that and divide by 2 pi. Okay? Everyone okay with this? All right.
Can you send that to the group?